Here, we'll record it now. Hello, if you're watching the recording, good day. We already started without you, but honestly, I just read this part so you could read it yourself. Work on these slides. Okay, so to the right, we see the model. Previously, guys, we identified a sine model for the height of the Ferris wheel in meters over time in minutes, right? That's what we had done previously. And we got this. We said the height over time is equal to 79 sine of pi over 15 t minus c. And notice, guys, c is that value that we left there, right? Plus 89. So what was all this? Remember, 89 was our midline. 79 was our amplitude, how far up and down it goes. And then pi over 15 was something that resulted from the period. The period of this Ferris wheel is 30 minutes. It takes 30 minutes to go around. And so in our notes about the equations of sine functions, we saw that period was equal to 2 pi divided by this value here, b, right? Or that this value b here was equal to 2 pi divided by the period. That should be in your notes, and we will see that more in the future. So previously, y'all, we observed that the sine function, right? You can see here, the sine function starts at angle 0, right? 0 radians, 0 degrees, whichever one you're using, it starts at 0, right? So it starts here at the midline with an upward trajectory. Do you guys notice that? Like, notice how if I go along the unit circle, it starts going upward first rather than downward. That kind of matters, right? Because if I'm starting over on the left side, then I would be going downward. But because I'm starting on the right side, I'm going upward, right? As I go counterclockwise. Now notice that the Ferris wheel does not start at that position, right, guys? The Ferris wheel starts down here at the minimum. It starts down here, right? So what I want you guys to be doing is thinking about where does the high roller of the Ferris wheel start its path? Where is it at time equals 0? Is it at the midline with an upward trajectory, right? That would be the right side of the Ferris wheel. Is it at the midline with a downward trajectory? That's the left side. Is it at the minimum? Is it at the maximum, right? So you can answer that there. And then I want you guys to think about what time would the high roller be at the midline with an upward trajectory? How long would it take for the Ferris wheel to reach the same positioning as the sine function starts? All right, y'all. So thinking about these two things, I'm going to give you guys a couple 2 minutes or 1 minute to think about and answer that right now. Okay. So we're thinking about where does the high roller start its positioning? Where does it start its path? And then how long would it take for it to be at that same starting point that the sine function starts at? I think the cord that I'm trying to use to charge my headset's kind of busted. Feels bad. Let's see what people are saying here. So I got a couple people with that multiple choice. I did kind of give you guys it away. So it's asking, where does the high roller start its path, y'all? Like, I see people changing it. Where does the high roller start its path, right? Not the sine function. The sine function starts at the midline going upward, right? The high roller, guys, notice it starts down here at the minimum, right? You see that? See how it's starting down here at the minimum? Now, how long would it take for this guy to reach that midline there, right? You guys see right here, this is essentially right here to the right is where the sine function starts. So how long would it take to reach that midline? Well, it takes 15 minutes to reach the maximum. So we could probably deduce that it takes 7.5 minutes, right? That's what a lot of people are saying, 7.5 minutes. So guys, do you see what I mean? It takes 15 minutes to go from the minimum to the maximum on the Ferris wheel, right? So how long would it take to go to the midline? It'd take half that, 7.5 minutes. Alrighty. So what I'm going to do now is I want to move us to the 5th slide. I'm going to actually stop the pacing thing. I dislike having a kind of, I don't know. I feel like it's like an abuse to to be able to just control literally your screen. I like you guys to have a little bit of choice in life, even if I'm still telling you where I want you to go. I would prefer if people have the choice to listen to me or not listen to me than to literally force them to be on the slide that I want them on. Okay, so guys, we're on slide 5. So check it out, man. We've got this. This is the graph that of our function that we had previously made, right? So, and it still has the C in here, right, guys? So let's see what this says. It says the C value in our sine function models an idea called the phase shift. Okay, guys, so that's what today's all about, phase shift. Essentially, the phase shift moves our periodic function left and right, okay, along the period. So what we're going to do is I want you guys to take some time and you're going to just kind of explore this a little bit. And I want y'all to move the slider below, because what that does is you see how the slider models C. So I can change the value of C in order to move the function left and right. You see that? So I want you guys to move it around until you find a point or a value for C, which makes our model start at the minimum. Anyone have any ideas? Why is it that we want our model to start at the minimum? Why do we want our model to start at the minimum, y'all? Go ahead and think about it for a second and post in the chat, y'all. And if someone's already answered, feel free to still answer, y'all. I like to see multiple people answering. That's where what starts. Ooh. So Christopher, or someone asked me, well, I gave it away, sorry. So Christopher says, because it's a sine function. So it is a sine function. And so actually, that's a good question to bring up. Because this is a sine function, when C equals 0, it starts at the midline. Do you see that? See how when X is 0, I'm at my midline? That is why it's there, because the sine function starts there, right? So then what we do is we say, well, the sine function might start at the midline, guys, but where does our Ferris wheel start? And it's like what Lanisha said. She said the Ferris wheel starts at the minimum, right? Remember, that's what we were saying here, y'all. See how the Ferris wheel started at the minimum? So we want to move this function such that the minimum, right? I could actually technically make any of these minimums do it, y'all. But I want my minimum to be at X equals 0, right? So I want you guys to take some time, mess around with this. And then I want you guys to experiment. Are there multiple values of C which work? Go ahead and take some minutes, take a couple minutes, play around with the C value there, y'all. And then go to the next slide when you feel like you've got an idea of like what C values work, and you can answer those questions and read along. All right, y'all. So I'm gonna give people 4 minutes, and then we'll check back in. All right. So at 11:25, go ahead and we'll come back. All right, guys. Okay. By the way, guys, if you moved your graph, right, or you zoomed in and out and you want to get back to where it originally was, just press that home button on the graph. Do you see that? And it'll take you back to the default. The home button that's on the right side of the graph. Okay, guys, so try to go ahead and take the next 10 seconds to wrap up what you're thinking so we can come on back. And I'm going to be having some people share what they've observed, please. All right. So please be ready to share your ideas. If you found the C value that works, guys, go ahead and post it on slide 6, please. If you found a C value that works, post it on slide 6 so I can kind of see what people are finding. If you already posted on slide 6, thank you very much. It's helping me out to see kind of what people have done. All righty, let's go ahead and take a look at what people got here. So I'm going to share my screen again. I'm going to share my screen again. And then let me pull up my chat. Cool. Where are we in life? So guys, don't worry about changing your answers right now or anything if you like see someone else's answer or something like that. So we're going to go ahead and just look at some of these and see what we see. So I see let's see, I see multiples of 30, also 0. Interesting. Yeah, wait, hang on. I just want to show you guys something real quick. The starting position was 0, guys, right? Remember when C was 0, we started at the midline, but recall that our goal was to start at the minimum, right? We wanted it to start at the minimum. We want this minimum brought to the y-axis where x is 0. Okay, guys? So what do we got here? What do we got? We got 7.5. I see a lot of. Let's look at what 7.5 looks like. So guys, if I move C to 7.5, where does it look like my minimum is at x equals 0, y'all? Does that look about right? Yes, yes, yes. And look, you can see 0, 10, and that was the minimum value of our Ferris wheel. It was at 10. Remember that? Cool. So 7.5 works. And really, guys, 7.5 was what we found in slide 4. For a lot of people said that it would take 7.5 minutes to reach that midline, right? So what we're doing essentially, guys, in this phase shift right here, y'all, is we're shifting it by 7.5 minutes, right? We're shifting the sine function by 7.5 minutes to match the fact that it takes 7.5 minutes for the Ferris wheel to reach the midline, right? So because a sine function is always supposed to start at its midline, check this out, guys. Watch, I'll show you something. What happens when x is 7.5? What's my y coordinate? It should be the midline, 89. And look, there it is. It actually is on the graph right there, 7.5 comma 89. Do you see that? So by having shifted it over to the right by 7.5, right, by plugging 7.5 in for C, we have essentially moved our sine function to match up with the model. Now, I asked you guys to experiment and see if there were multiple values of C which worked, though, right? So let's see what happens. Are there multiple values of C which worked? What else did people get? We got, I see some people with 37.5. Hey guys, why? Before I even do it, 37.5 versus 7.5, which is what we had before. What's the difference between those? What's the difference between those two values? 30 more, right? 30 was a very relevant number for us. Remember, guys, what was 30 related to in our model? What was 30? Where did 30 come from? Period. It's the period. Exactly. Thank you. Thank you, Millie. Thank you, Fernando. So guys, notice that 30 minutes is the period. So if I shift it to make it correct, right? Like we did here. And then I add another 30, what happens, right? If I add a full period to my phase shift, so I get to 37.5, watch what happens. I'm in doesn't this look the exact same? Look at when I switch between them, did anything change? Has anything changed here? Do you see? Isn't that kind of interesting? Watch. If I do any other number, it changes, right? Do you see that? But these two numbers are the same. Would minus 30 work? That's a good question. So what would be the value then, Hong, if I did 7.5 minus 30? What would be my value for 7.5 minus 30? It would be 22.5, negative 22.5, sir. So math is not the answer, Hong. So it'd be negative 22.5. And look, it's the exact same. So what's interesting, guys, is because these are periodic functions, right? So they repeat themselves every period. What's happening with the phase shift is that we're moving it by a fraction of that period in order to match it up, right? But if I moved something a whole period, right? Like if I take c equals 0, right, the original, and I make it so that it's c equals 30, it won't change at all. Do you see that? Nothing changed. Even if I make it negative 30, nothing changes because I'm doing it in whole periods, right? I'm moving it in a whole period. And if something is a wave, right, and it repeats itself infinitely, then shifting that over one full period will literally not change anything visually because it's still going infinitely the exact same pattern. You see that? It's kind of an interesting thing that happens with this. So what we observed, y'all, was that moving the phase shift based on how long it would take to get to the midline, it works not only in the positive direction, it also works in the negative direction. Watch, I can move it so that my minimum is there using a negative number. By the way, guys, notice that it's actually x minus c. So if it's negative, it kind of is adding, but that's kind of a weird relationship about transformations of functions that you guys might have observed in algebra 2. And I'm not about to waste my time going over it. But yes.
So
yeah.
Can this be 37.5?
Yes, it could be 37.5. Can anyone think of any other numbers that it could be? Other than we had, let's see, what have we done so far? Negative 22.5, 7.5, and 37.5. Could there be any other numbers? 67.5, exactly. 67.5 is just adding another period, right?
Yeah.
97.5, add another period. You could literally do this infinitely, guys. In fact, I can generalize it by saying 7.5 plus 30k, where k is just any whole number. So literally, if k is, 10, then I add 300.75. If I make c 300.75, it literally is still the same. It's still the exact same. So it's interesting, guys. It repeats itself with each period. Now, typically, y'all, we are going to solve for it probably in terms of just within one period. How far does it need to go? How far does it need to go within one period in order to match up? That's usually what we're going to do. But technically, if you wanted to be kind of annoying, right, on a test, if you wanted to be annoying and you gave me a value where it was like, minus 97.5, I would have to give you full credit because it's technically true. So that's something that you can mess around with. Haha, fun math jokes. Am I right, y'all? We love those. So that was our thing there. So then, guys, what I want y'all to do is think about, so in general, we can solve for the phase shift of a periodic model by considering two things. First of all, the fact that the sine function begins at the midline with an upward trajectory by default. I keep saying upward trajectory, guys, because I want y'all to realize that this here, this value over here at 22.5, 89. Notice that's at the midline also, but it's going downward. Do you see that? It's like as I keep going, it's going downward. The sine function doesn't start there. That would be like a negative sine function because it'd be going down. So it's just kind of like a thing to observe. It's going upward, right? So that's the first thing to observe. And then second, you just look at, well, if I consider my model, when does my model reach that point where it's the midline going up? And if you can figure out how long it takes to do that, that is your C value. You can even, as we saw it before, guys, you can do negatives. Like, for example, if it's easier for you to consider, okay, how long ago was I at the midline, right? That's negative time, isn't it? So like if I look at my Ferris wheel and I, for some reason, wanted to say, okay, well, instead of it takes me 7.5 minutes to get here, it takes me, I was there already. If I look backward by 22.5, I guess if that makes sense in the context, then you can always use that. So that's going to be how we can find C. So then looking at this one here, guys, I want you to think about it. To the left, we have the sine function graphed in blue. Oops. So you see the blue, that's the sine function. And then the cosine is in red. So cosine and sine, as we saw before, guys, they had the exact same period, the exact same amplitude, the exact same midline. So all that's different between them must be a phase shift. So I want y'all to think about and calculate what would be the phase shift necessary to make it so that cosine matches up with sine, to make it so that cosine equals sine. All right, y'all. So take a minute, think about that, and try to figure out what C would be here. I see some of y'all doing this already. How dare you? Just kidding. Har har. Let's see. What are people thinking? Ooh, 0.1/2. Ooh, yo, guys, notice. Look at what the scaling is on your x-axis. It's not going by 1, right? Look at the scaling, y'all. Look at the scaling. Okay, it's not 1/2. But you're close in idea if you're thinking 1/2, right? You're really close. Let's see what people think. We got 1/2 pi. Look at that. Min said it out here. I mean, a lot of people have said it, but like this is kind of like, so everyone who's thinking 1/2, you're thinking 1/2, right? Because you're seeing that it's half, that the midline for the cosine, right? The one in red here, you see that, the midline? You're seeing that it's halfway. It's halfway towards getting there, right? So we need to shift it over by 1/2, right? But 1/2 of what? Well, we're measuring in terms of pi here, y'all, right? Remember, guys, it's going to be pretty common with a trig function to measure your x-axis in terms of pi, because that's the period. The default period is 2 pi. Remember that? It takes 2 pi radian to go around the unit circle. So therefore, it takes 2 pi radian for the cosine or the sine function to repeat itself. Okay, so in the end, y'all, C here would be pi over 2. You see that? And I can actually show y'all if I have a, let's get rid of all these things. What if I have sine of x and then I have cosine of x, right? And let's go to a regular Desmos graph. If I have sine of x and then I have cosine of x, you can see that cosine, its midline is at negative pi over 2. So if I make this instead cosine of x minus pi over 2, check it out. They are now matched up with each other, right? You see how they are the exact same graph? So actually, in general, we can literally claim that cosine of x minus pi over 2 is equal to sine of x. This is literally this is an identity that's true. No matter what x is, it's always true that cosine of x minus pi over 2 is equal to sine of x, which is kind of interesting. I think it's interesting. I don't know about you guys. No, I'm just kidding. I know you guys think it's interesting. You don't have to tell me. You don't have to tell me because I know it's true. All right, y'all. So here's what's up with us. I really want to do this one. I really want to do this exit ticket. So guys, I would like to make sure that people can do the exit ticket before class is over today. So I'm going to go ahead and skip this thing, completing the week 4 classwork. It was basically just what we were going to do is if you click it, it was going to have us, I was going to have us finish what we were working on slide 4, where it was asking us kind of for phase shift of these different scenarios. But I'm going to go ahead and say, let's do this exit ticket instead. All right, y'all. So go ahead and please take some time, y'all, thinking about it. In this exit ticket, ask questions, by the way, if you have any questions while you're working on it. In this exit ticket, we're talking about weather in Oakland. We're actually specifically talking about cloud coverage. So we're talking about kind of like how clear versus cloudy are the skies. So in general, Oakland has a minimum sky clarity, right? Like kind of like a measurement of how clear are the skies. We have a minimum in January and we have a maximum of clear skies in July. And so actually what you can see is it goes from minimum to maximum, and then it would go back down to the minimum as it repeats year after year. It's a periodic function, actually, right? It's a periodic model. And so what we can do is we can actually use these values to derive a trig function, a sine function, which models essentially the clarity of the skies in Oakland over time. And then you can use that model to make kind of different predictions, which is kind of cool. So I would like you guys to go ahead and try that. Find the amplitude midline period first, because that's what we're used to, right? That's what we're kind of we've been doing. And then go ahead and try to think about what would be the phase shift, right? This one I think is a little challenging, y'all, but I think you guys can do it if you use some brain power. All right. You might want to draw a picture. If this picture is not enough, you might end up wanting to draw a picture to think about it. And then I've given us the general sinusoid again here, y'all. So that way you can put all this information together to create the equation, which models it. So I want people to please go ahead and finish this exit ticket before leaving class today. When you're done with it, go ahead and let me know so I can kind of check what your work is looking like. And otherwise, we will be good. Don't worry about this week 4 classwork thing. I think what I'm going to do is I'm just going to give people their credit for it based on the first 3 slides, and I'll skip the 4th slide. If you'd like to try the 4th slide for the practice, I will not stop you at all, and I will give you feedback on it if you did it. Since they're percentages, would we turn them into decimals? That's a good question, Mila. Since we're gonna always be, since we're talking about, like, this is like the percentage is kind of like the measurement here. You could do that, but I'm not going to make you, because I think it'll be nicer to work with the numbers 45 and 92 instead of 0.45 and 0.92. So just go ahead and work with them as 45 and 92, and we recognize that we're working in percentages. Would the period be 1 year? Yeah, it would be, Victoria. However, notice that we're measuring time not in years, but in months. So what would our period actually be? Do we submit the week 4 assignment if we don't do slide 4 or leave it? Oh, on Google Classroom. Yeah. You guys can just go ahead and leave it, honestly. If you want to submit, go ahead, but I'm just going to grade them all anyways, even if you haven't submitted it. Since it's been that one has been such a weird assignment that I've kind of left and kept skipping to finish. If you'd like, you can, if you are a completionist, you can go to Google Classroom and submit it right away. I'm going to stop sharing my screen because I don't think you guys really need to see that. So actually, I'm going to stop talking because you guys are focusing. Wow, Stephanie, how dare you? Working on other homework? Come on, bro. You better be done on this already. I'm looking at it. It's blank. Hello? Team? Now I think about it, I can just turn off the recording also. I feel like we're done. We're kind of done here. I'll leave it on. Why not? Hong asks, is there a formula for phase shifts? That's why I would say phase shifts are typically the harder part of these trig models, because they kind of have, it's a little bit harder to come up with like a formula. It's more like what we were talking about there on slide 6, where it said, in general, we can solve for the phase shift of a periodic model by considering two things, right? The first one was that we observe that the sine function begins at the midline. And then we look at our kind of like our model and we kind of try to figure out, well, where is the midline, right? When is the midline? So for example, in this model that we have, we said that January was time 0. July is time 6 months, right? Because it's 6 months after January. If that's the minimum and the maximum, where do you think the midline would be, right? Where would be the midline if January is the minimum and July is the maximum? Ooh, yes, it would be, Christopher. Yes, Hong. Exactly. Y'all are on the right path. So remember, guys, we're looking for the midline, right? Where's the middle? The midline is always between the minimum and the maximum, right? So if our minimum is at time 0 and our maximum is at time 6, where would be the middle?
So the formula shouldn't be
hang on a
the
second, Millie. I'm real. I can't hear you. I've been having a little bit of technical difficulties out here today. Okay. Talk again.
My hair is a little bit loud. I hope you can hear what I say.
Yeah, I can hear it.
I was saying, shouldn't the formula be the maximum minus the minimum and divided by 2? Just like how we get 3.
Oh, you mean the time of the maximum minus the time of the minimum divided by 2? Ooh, that's not a bad way to put it. Yeah, that's a good formula to use. That could work. That could work, definitely. If we know when the maximum is and we know when the minimum is, then it would be in between those. The reason, I guess, yeah, that's a great way to put it. That's a great way to put it. Would it be the minus? No, it would be an average of them. You would add them, actually. You would look at the time of the maximum plus the time of the minimum and then divide by 2, and that'd be in between them. The only thing that I want to say with that, Millie, to be careful, is remember we're looking for the midline that that's going upward. So it should be between the minimum on the left and the maximum on the right, rather than reversing it, right? Because notice if I go on the opposite way, right, then I would be at the midline going down, which is not the sine function. So should we put months for the unit of the phase shift? Yeah, that's a good thing to do when we're talking about things such as a context in the real world. It's useful to use your units. By the way, guys, at this point in time, if you've finished the exit ticket, where our classes has reached, it's 11:52, so we're done with class. So you are welcome to say your goodbyes and head on out. If you want me to check your work right now, I can. I will be checking these from people outside of class. Yeah, let's see. I'm gonna bye y'all. Christine asked me to check hers, so I'm gonna share the screen while I check hers. So let's see, Christine, what did you do? You said the amplitude would be the maximum 92 minus the minimum 45 divided by 2, and that gave you 23.5. Will I leave comments? Yeah. I will be. And in fact, I'm still recording it actually. So if you really want to see what I'm saying to Christine right now, you can just look at the video when I post it at the very end. Bye. So let's see. So that's your amplitude. That makes sense. Your midline, you found the average of them. Cool. Sounds good. The period is 12 months. Looks good. Right. And then finally, she said the phase shift would be March/3. I assume you mean like March or 3, like they're the same thing. Fun fact, March is not 3 months after January. You're thinking of April. But yes, it would be 3. I get where the confusion is. This is where like sometimes it can be hard like to think. This is why we have to set what is time 0, right? Because a lot of times we're used to thinking of the first thing as being 1, right? Like January is the first month of the year. But if I want to have there be a time 0, right, and that's the start, then I kind of have to consider January as time 0, right? And then yeah, you see what I mean? You could, but you know what's interesting is you could technically make January time 1, right? T equals 1, in which case December of the previous year would be time 0, right? And all that's going to do is just shift kind of our values, right? So then now my minimum is at time 1, my maximum would be at time 7, and so my midline would be at time 4, which is still April. But because we've defined January as time 0, it's all shifted over 1. Okay. So then finally you put it all together. And so you said amplitude is 23.5. So you put it there. Excellent. You said the midline was 68.5. Excellent. Remember, the period is not the B value, right? B is 2 pi divided by the period. If my period is 12 months, then 2 pi divided by 12 would be 2 pi divided by 12, right? Which would be equal to pi over 6. You see that? So that'll be the correct one. And then -3 because that was our phase shift.